Hello friends, we will discuss today about atom and its structure. All matter is made up of atoms. An atom is a tiny solar system. In the center of the atom is the nucleus, which is a cluster of protons and neutrons. The protons have a positive electric charge, while the neutrons are electrically neutral. The nucleus makes up almost all of an atom's mass or weight. Whirling at fantastic speeds around the nucleus are smaller and lighter particles called electrons, which have a negative electric charge. An atom has the same number of electrons with negative charge and protons with positive charge to make the atom electrically neutral. An extremely powerful force called the nuclear force holds the protons together in the nucleus as they naturally repel one another electrically. The atom of each chemical element have a different nucleus. An atom of hydrogen has one proton and no neutrons. An atom of helium has two protons and two neutrons. Heavy elements have a large number of protons and neutrons. For example, the most common isotope of uranium, uranium-238, has 92 protons and 146 neutrons in its nucleus. Matter has mass and takes up space. Atoms are basic building blocks of matter and cannot be chemically subdivided by ordinary means. The word atom is derived from the Greek word atom, which means indivisible. The Greeks concluded that matter could be broken down into particles too small to be seen. These particles were called atoms. Never trust an atom. They make up anything and everything. Friends, as we have discussed, atoms are composed of three types of particles: protons, neutrons and electron. Protons and neutrons are responsible for most of the atomic mass. For example, in a person weighing about 149 pounds, 15 OZs are protons and neutrons, while only 1 OZ is electrons. The mass of an electron is very small, that is about 9.108 into 10 raised to minus 28 grams. It is the number of protons that determines the atomic number. For example, hydrogen is 1. The number of protons in an element is constant. For example, for hydrogen is 1 and for uranium is 92. But neutron number may vary. So, mass number, that is protons and neutrons, may vary. The same element may contain varying numbers of neutrons. These forms of an element are called isotopes. The chemical properties of isotopes are the same, although the physical properties of some isotopes may be different. Some isotopes are radioactive, meaning they radiate energy as they decay to a more stable form, perhaps another element. Half-life is the time required for half of the atoms of an element to decay into a stable form. Another example is oxygen, with atomic number of 8, can have 8, 9 or 10 neutrons. Ancient theories of reality. Various scientists and researchers have put their view about atom. Thales viewed atom as everything is ultimately water. Anaximander defined atom as air. Heraclitus discussed atom's form as fire. Pherecydes has given concept of atom as earth. Empedocles has defined it as water, air, fire and earth, and said that everything in reality made of various combinations of this. Democritus took a different approach, as ultimate constituents are something unfamiliar to us, so not inconsistent with anything in reality, and defined it as theoretical posit. But Aristotle endorsed Empedocles' theory, and his views prevailed until 17th century. Historical models of an atom. Bohr model. Bohr model shows electrons circling the nucleus at different levels or orbitals, much like planets circle the sun. Electrons move from one energy state to another, but can only exist after definite energy levels. The energy absorbed or released when electrons change states is in the form of electromagnetic radiation. The wave model and quantum theory. The Bohr model was only able to explain the very simplest atoms like hydrogen. Today's modern day theory is based on mathematics and the properties of waves. The wave model forms the basis for the quantum theory. This theory gives the probability of locating electrons in a particular location, unlike assuming electrons orbit the nucleus as in the Bohr model. Theoretical models. A goal of nuclear physics is to account for the properties of nuclei in terms of mathematical models of their structure and internal motion. Three important nuclear models are the lipid drop model, the shell model developed by Maria Geoffert Mayer and Hans Jensen, which emphasizes the orbits of individual nucleons in the nucleus, and the third collective model developed by H. Bohr and Ben Mottelson, which complements the shell model by including motions of the whole nucleus such as rotations and vibrations. The liquid drop model treats the nucleus as a liquid. Nuclear properties such as the binding energy are described in terms of volume energy, surface energy, compressibility, etc., the parameters that are usually associated with a liquid. This model has been successful in describing how a nucleus can deform and undergo fission. The nuclear shell model is similar to atomic model, where electrons arrange themselves into shells around the nucleus. The least tightly bound electrons in the incomplete shells are known as valence electrons because they can participate in exchange or rearrangement, that is, chemical reactions. The shell structure is due to the quantum nature of electrons and the fact that electrons are fermions, particles of half integer spin. Particles with half integer spin are bosons. A group of bosons all tend to occupy the same state, usually the state with the lower energy, whereas fermions with the same quantum number do just the opposite. They avoid each other. Consequently, the fermions in a bound system will gradually fill up the available states. The lowest one first, then the next higher occupied state, and so on up to the valence shell. In atoms, for example, the electrons obey Pauli's exclusion principle, which is responsible for the observed number of electrons in each possible state, at the most 2, characterized by quantum numbers n, l, and m respectively. It is the Pauli's principle based on the fermionic nature of electrons that gives the periodic structure to both atomic and nuclear properties. Since protons and neutrons are also fermions, the energy states the nucleons occupy are filled from the lowest to the highest as nucleons are added to the nucleus. In the shell model, the nucleons fill each energy state with nucleons in orbital with definite angular momentum. There are separate energy levels for protons and neutrons. The ground state of nucleus has each of its protons and neutrons in the lowest possible energy level. Excited states of the nucleus are then described as promotions to nucleons to higher energy levels. This model has been very successful in explaining the basic nuclear properties. As is the case with atoms, many nuclear properties, for example, angular momentum, magnetic moment, shape, etc., are dominated by the last filled or unfilled valence level. The collective model emphasizes the coherent behavior of all the nucleons. Among the kinds of collective motion that can occur in nuclei are rotations or vibrations that involve the entire nucleus. In this respect, the nuclear properties can be analyzed using same descriptions that is used to analyze the properties of a charged drop of liquid suspended in a space. The collective model can thus be viewed as an extension of the liquid drop model. Like the liquid drop model, the collective model provides a good starting point for understanding fission. In addition to fission, the collective model has been very successful in describing a variety of nuclear properties, especially energy levels in nuclei with an even number of protons and neutrons. These even nuclei can often be treated as having no valence particles so that the shell model does not apply. These energy levels show the characteristics of rotating or vibrating systems expected from the laws of quantum mechanics. Commonly measured properties of these nuclei, including broad systematic of excited state energies, angular momentum, magnetic moments, and nuclear shapes, can be understood using the collective model. The shell model and the collective model represent the two extremes of the behavior of nucleons in the nucleus. More realistic models, known as unified models, attempt to include both shell and collective behaviors. Structure of atom. As we have discussed previously, atoms are the basic unit of matter and the defining structure of elements. Protons and neutrons are heavier than electrons and reside in the center of atom, which is called the nucleus. Electrons are extremely light in weight and exist in a cloud orbiting the nucleus. The electron cloud has a radius 10,000 times greater than the nucleus. Protons and neutrons have approximately the same mass. However, one proton weighs more than 1800 electrons. Atoms always have an equal number of protons and electrons, and the number of protons and neutrons is usually the same as well. Adding a proton to an atom makes a new element, while adding a neutron makes an isotope or heavier version of that atom. Nucleus. The nucleus was discovered in 1911, but its parts were not identified until 1932. Virtually all the mass of an atom resides in the nucleus. The nucleus is held together by the strong force, one of the four basic forces in nature. This force between the protons and neutrons overcomes the repulsive electrical force that would, according to the rules of electricity, push the protons apart otherwise. Protons. Protons are positively charged particles found within the atomic nuclei. They were discovered by Ernest Rutherford in experiments conducted between 1911 and 1919. The number of protons in an atom defines what element it is. For example, carbon atoms have 6 protons, hydrogen atoms have 1, oxygen atoms have 8, and nitrogen atom has 7 protons. The number of protons in an atom is referred to as the atomic number of that element. The number of protons in an atom also determines the chemical behavior of the element. The periodic table of the elements arranges elements in order of increasing atomic number. Protons are made up of other particles called quarks. There are 3 quarks in each proton, 2 up quarks and 1 down quark, and they are held together by other particles called gluons. Electrons. Electrons have a negative charge and are electrically attracted to the positively charged protons. Electrons surround the atomic nucleus in pathways called orbitals. The inner orbitals surrounding the atom are spherical, but the outer orbitals are much more complicated. An atom's electron configuration is the orbital description of the locations of electrons in an unexcited atom. Using the electron configuration and principles of physics, chemists can predict an atom's properties such as stability, boiling point, and conductivity. Typically, only the outermost electron shells matter in chemistry. The inner electron shell notation is often truncated by replacing the longhand orbital description with a symbol for a noble gas in brackets. This method of notation vastly simplifies the description of large molecules. For example, the electron configuration of beryllium Be is 1s2, 2s2, but it is written helium to s2. Helium is equivalent to all the electron orbital in a helium atom. The letters S, P, D and F designate the shape of the orbital, and the superscript gives the number of electrons in that orbital. Neutrons. Neutrons are uncharged particles found within the atomic nuclei. The neutron's mass is slightly larger than that of a proton. Like protons, neutrons are also made of quarks, 1 up quark and 2 down quarks. Neutrons were discovered by James Chadwick in 1932. isotopes. The number of neutrons in a nucleus determines the isotope of that element. For example, hydrogen has 3 known isotopes: protium, deuterium, and tritium. Protium, symbolized as 1H, is just ordinary hydrogen. It has 1 proton and 1 electron and no neutrons. Deuterium, also symbolized as capital D or 2H, has 1 proton, 1 electron and 1 neutron. Tritium, symbolized by capital T or 3H, has 1 proton, 1 electron and 2 neutrons. Characteristics of atom. Friends, to study exactly what atom is, it is essential to know something about its characteristics, as atom itself was and still defined based upon its dynamic characteristic. For a typical atom, it has following characteristics in general as solid, everlasting and indestructible, come in finitely many different shapes, an infinite number of atoms of each shape, and lastly, shapes of atoms account for coherence with other atoms and for sensible effects. Besides, it has its own shape, size, hardness, weight, location, taste, smell, temperature, sound and color as primary qualities. Atoms have no secondary qualities. Things have secondary qualities only because of the arrangement of these atoms and because of the interaction between these atoms and our sense organs. Summary. Friends, now it is a time for us to summarize what we have learned and discussed in details. I hope that you might have enjoyed listening and observing about this indivisible particulate matter. We too have learned about its detailed structure along with some examples. We have further discussed about the ancient theories of realities, historical and theoretical model of atom, right from its discovery to the present perspective of modern structure as well. Lastly, we understood the structure with reference to the characteristics as primary qualities and have no secondary qualities. Things have secondary qualities only because of the arrangements of their atoms and because of the interaction between their atoms and our sense organs. Thanks.